Hello guys, Cyprien from FE Overhaul here. So in today's video, we'll have a look at how to do this kind of steady-state thermal analysis in Salome Meca and using the Aster solver. So I'll show you the step-by-step process to assign the loads, create the mesh, and do everything you need in order to get this kind of results. So let's start. So as per Salome Meca, I'm using currently the Windows version that you can download for free on this website, codeasterwindows.com. And you go in the download section, and I just downloaded the latest one, the download Salome 2019. And I think there is some kind of fix on it that solved some previous bug. So make sure you download the latest one. Okay, so now I just opened Salome Meca, so I'm starting from a blank slate. And you see that in this new 2019 version, you have the new Salome Shaper module, which is very nice to do parametric CAD. In my case, I will not do the CAD into this video, so I'll just go into the classic Geom module, in which I will import my, my model. So let's go and import the step file. And the first thing you see, so you have to click here to reset the view. First thing you see is that it's imported at one part. So it's not a part, it's a compound actually. So all the parts you have inside are actually available, but you have to explode this model in order to see them into the object browser. So let's do that. Let's go to New Entity, Explode. And you see you can explode them into solids. And if you do that, the parts will appear here. Now, one thing which is important is that if you hide some of those parts, you see that there is no interface in between this board and the part into this CAD model. So we have to create that in order to be able to simulate it in Salome Meca. So in order to do this, it's actually pretty simple. You just go into operations, and you have partition. And this partition feature is really useful. Just select all the parts here with shift pressed. You can select everything, the 8 objects. Just click on apply and close. And you'll see that you'll get a new object called partition, which this time will also contain the same thing, but with the interface in between. So I have to explode it again. And if now I hide the part like that, you see that I am now seeing the interface between those parts. So that's nice. Now, the other thing to note is that previously the parts were called with the correct name, but now the name has changed by doing the partition. So I have to rechange the name by clicking on it and just rename it. So for example, this one will be part 14. So I'll do that, and then we'll go to the next step. So the next step usually is to create the groups that will be used to assign the boundary conditions to this model. So for that, you have to understand what are the boundary conditions applied to this. And basically, what I'll do is that I will apply a power condition to generate heat coming from each of those chips on this board. And there will be a convection applied to the faces of this heat sink. So in order to apply the power, I will apply it to as a volumic type of load. So I do not actually need to create a group. The groups will be created automatically, as you will see. For this condition, to apply the convection, I do need to create some groups. So let's go forward, and I'll show only the heatsink for to assign the groups more easily. Let's go to New Entity, Groups, create a group, choose a surface group, select everything, rotate that, and then press Shift and select this face here. You don't see it, but if you show only selected, you'll see that this face at the bottom will be unselected. Apply and close. Okay, please. Okay, I forgot to put the shape into it, so I have to select all that and add, yeah. Okay, add and close. So now I created this group, so I can rename it also. I call that heatsink, or maybe convection. Yeah, okay. So the part on the Geom module is now over. So I'll display everything again. And I'll go to the meshing steps. So let's open the Smesh module in the top bar here. And with this module open, the first thing will be to create some mesh from each of these parts. And I will use the parts created from this partition. So select everything with Shift pressed on your keyboard and click on this first icon, Create Mesh. And now let's select the algorithm. So I will use the NetGen 1D, 2D, 3D algorithm, which is the easiest to mesh everything using tetra elements. And for the hypothesis, also I will use the basic default options. Apply and close. Now you see that it has generated 8 different mesh sets. And now I have to click on each of them and click on compute to actually have them displayed on the screen. So I have to do that one by one. Okay, so now I generated all the mesh for this simulation. Now, you do not need to worry that the mesh elements from one side is not necessarily merged with the nodes on the other side. We will use a special function in the code Aster to automatically create the contact with those faces. So we can have separate mesh sets. That's not a problem. Now let's have a look at merging all of that into one mesh, because I cannot import 8 mesh sets together. So I have to create what is called compound mesh. And when I create a compound mesh, it will import the mesh groups from each of those mesh sets. So what I have to do first is to create the mesh groups for the mesh sets here, and then merge all that together. Now, what you note also is that those mesh sets have names which are not very convenient. So I will also rename all of this in order to recognize them more easily. And I will name them the same as the geometry. Okay, now that this is done, let's create the group for the mesh for the convection that I will need for the heatsink. So let's select the heatsink mesh set, go to mesh and create group from geometry. And let's select, so let's find the geometry of the heatsink and select the convection. So note that it's important that you create this geometry group under this heatsink part and not under the partition part, because basically the mesh I created here belongs to this geometry here. So the mesh group has to be also related to this. So if you did like I did in this video, you should have the correct answer. So click apply and close, and you see that now I have this mesh group. So if I display only this one, so show only, I should be seeing this, and as you can see, this face here, which is in contact with the bottom, is not selected. Okay, so now I will create the compound of all those mesh sets. So I'm selecting all of this, and I click on build the compound mesh. And when you do that, so I will not merge the coincident nodes and elements. So I unselect this option. So it's important. It's very important to unselect this. And it's also important to check this option, which is to create the groups from the input objects. And this will create the groups that will allow me to assign the boundary condition. So if you forgot each of them, you will have to recreate this compound. So apply, close. And if I show only the compound here, you see that I have now exactly what I need for my simulation. So just as a measure of precaution, don't forget to save your study. And what I like to do also is to export my mesh into a MED file. So just in case Salome Meca gets a problem or something and I'm not able to save, or who knows. So it's optional, but you know, it's better to have a save of everything. Now it's time to open the Aster Study module and to assign the condition for simulation. So let's go into current case, right click, add a stage to this simulation. And I'll be adding the function one by one. So you can either collect those small icons here, but the thing is that those names are not very well shown here, so it's a bit annoying. So what you can do also is do a right click on stage and you have the full name displayed here, which is much more convenient. So the first thing to do always is to read the mesh. So assign the read the mesh function, and in the drop down, find the compound mesh. And you see that this will be imported automatically. Click on OK. Next step is to assign finite element model. So assign finite element. Check this option, finite element assignment. Click on the plus here, and I'll assign the same model for everywhere in this model. And this will be a thermic analysis. And this will be a 3D type of thermic analysis. So that's all I need for the model. And now we go into the definition of the materials. So in order to define the materials, you have to understand the different coefficients and what kind of material I'll be using. So I put everything into an Excel file. So here it is. And I will have 4 different materials for this simulation: aluminum, silicon, glass, and thermal grease. So aluminum will be for the heatsink. The silicon will be for each of those chips, so 1, 2, 3, 4, 5. The glass will be for the PCB body, and also those small 5 parts which are included into the PCB. The thermal grease will be for this very slender part, which is in between the heatsink and the chip. Now have a look at the different options. So for thermal simulation, we only need 2 things in Aster: the thermal conductivity and the heat capacity. So if you do not have the heat capacity, but instead you have the specific heat like this, what you have to do is to multiply the value of the specific heat by the mass density, and you will get the heat capacity. Now, be careful about the units. All the units here are in meter, so SI units. So let's go and let's define all of that into code Aster. So the first thing to do is to create a new material. And you have a big list. So I'll change the name of the material called aluminum. And you have to find the model of material which is used for thermal analysis. So if you type heat into the search field, it automatically filters and find out the isotropic heat conduction. So this is what you need. So need to edit that and add the coefficients for this. So for aluminum, so thermal conductivity 238, and the heat capacity is 2.43 E6. Click on OK, and your material will be defined here. Now, because I will do the same thing 4 times and it's repetitive, so I will not put that in the video, but the procedure is exactly the same for the 3 next materials. So after creating those 4 materials, next step is to assign them to each of the parts. So material, assign a material. So select the model here, and I have to create like that 1 item for each of those parts. So, and you can select by using those group of elements. So for the part 14, 15, 13, 12, and for the chip, my material will be silicon. Then you click on the plus here to add another one. And for the heatsink, so if you select the volume here, it will appear here on the screen, so you see which is which. So I'm selecting that, the heatsink, and this one will be aluminum. Then the thermal grease, so TIM volume will have the grease material. And finally, the PCB will have the glass material. Okay, so material assignment is done. Now we come to the next part, which is the assignment of the loads. So here are the values of the loads that will be applied. So there will be one convection with a convection coefficient of 15 watt per meter square degree Celsius, and an ambient temperature of 20 degrees Celsius, and 3 power condition applied to the different parts. So the parts 11, 12, and 13 will have the same total power of 0.2 watt. The part 14 will have 0.05 watt, and the chip will have 20 watt. Now, the initial tutorial was putting it in total power value like this, but what is important is that in Salome Meca and Code Aster, it's a volumic value that you have to enter. So it's not the total power like that. So what you have to do is to calculate the volume of each of those parts, and then you have to divide it by the volume, and this is what you get in the volumic type of source. So this is the value of the volume of the different parts, and let me show you how I got that. I calculated it from here. So I'm going back very briefly into the meshing module, And if you go into measurement, so you have basic properties, volume. And if you select, so you have to go like that in the mesh, select, for example, part 14, compute, and you get the value of the volume. So just do that for all these parts, put it back into the Excel. Here, divide those value of total power by this, and you get this value. Okay, now let's assign all of that into Aster Study. So back to Aster Study. Let's go and assign BCN load, assign thermal load. Okay, so let's assign the convection first. So convection is here, échange, exchange. So that's the convection load. And edit this. So select the heatsink volume. Sorry, not the volume. So this time, this is why we created this group, convection. So that's what you have to select. It's a surface type of load. And here in the we have to assign the coefficient H, which is 15, and external temperature, which is 20. Okay. Now let's assign the power for the other. So I'll assign first for the part. So that's for the part 14. Like that. So, and this is the value I'm taking here. Okay. So I'll do that again for the 3 other parts. I will cut that from the video because it's repetitive. Okay, done. So at the end, you should have 5 power conditions and 1 convection condition. So they all correspond to what I have written here in this Excel file. Now that this is done, click on OK. And we are ready to generate the thermal analysis case. So click on Analysis, Thermics, Linear Thermal Analysis. So we have the model, we have the material field assigned here, we have to add the load. So there's just one load here, but this load contains all the 5 boundary conditions. And that's all I need. Let's add additional results. So this will only calculate the temperature. If you want to have the flux of temperature, you need to add a calc champ command. So right click, go to post-processing calc champ. And don't forget to check this option, reuse the input object. So the name here will be the same. This is important. And check this option, thermic. And here you can add other types of results. So we'll add flux Elga. So this is the flux at the gauge points. Flux Lno at the element nodes. And flux nœud, flux at the node. So I'm adding all this. And now the last step is to add a way to generate the results. So right click, output, and set the output results. Here I need to create a file which will contain the results. So let's call it PCB results 2.rmed. So the extension I'm using is rmed because I will be creating a med file. So check this option, med, and here don't forget to attach the results to here. It's a classical mistake to forget to do this, and then you get nothing in the results. So check this result here, and this is done. Don't forget to attach this here. Okay, and now we're ready for computation. So to compute this model, we have to go in the History View tab here on the left. Select the stage 1. There's a plus here. Click on that. Check quickly the run parameters, and you might want to give it a bit more memory, depending on the size of this model. So I'll give it 4 gigabytes. And there is a time limit, so in case your model takes more than 15 minutes, it will automatically stop. So make sure you have enough time set here. And this will only work on one processor because this is not the MPI version. So we'll just use that. And now just click on run. And hopefully this will start to solve, and we just have to wait. So this can take quite a long time to compute, so I'll have to wait a bit. And what I noticed is that in this version of Salome Meca 2019, sometimes it still shows up as if it's computing, but when you click on this window, it actually shows up that, okay, there is a, okay, there is a problem. So, well, that's fine. So let's have a look. What is this problem? Oh yeah, right. I forgot to assign the contacts between the parts. So yeah. So let's go back, and there is something I forgot to do, and we'll be doing right now, which is to create the interface between each of those parts. So now the problem I got is that basically I set up everything, but I forgot to create a contact between these parts. So the nodes from this part and the nodes from the board have no way to communicate from each other. So I need to set up a way to communicate, and this is done using a type of load called Liaisons. So let's edit the load, and you have it here. So I forgot to set that up. Liaisons, click on the plus here, and let's create a different type of liaison. So liaison means a link in French. So the first is select the master group. So this will be the board. So PCB here. Let's create let's select all the elements that will be linked to this board directly. So this will be this one, the part 13, the chip, and the part 12. Okay. And that's all I need to do for the first one. So I need to create 3 liaisons like that. The first one. Second one will be in between the chip here and the thermal grease on top. So TIM volume. So it's a very slender type of layer that you get here. So I need to create that as well. Okay. And now I need to create another one for between the thermal grease and the heatsink. Okay. So now that this is assigned, okay, and I have nothing else to change, I can go back and launch again the computation. So hoping I didn't do any other mistake this time. So let's go back to current case and let's run that again. This will take some time, so let's wait and go back when it's finished. Okay, so now it's finished and it's green, which means that it's succeeded this time. Also, I realized that in this version of Salome Meca, you have to click on the run case to actually see it change to green, which is a bit weird. So sometimes if you don't click, it continues to run and you believe that this is not finished, but you have actually to click on it, so it stops and becomes green. So probably that's kind of bug, but okay, so let's talk about the post-processing of the results right now. So in order to post-process, so in the previous video I was using Paravis, and I was showing you how to look at the result in Paravis. Now in this version 2019, there is a big surprise for me at least, is that there is a post-processor now included into Aster Study, which is very, very nice. So to see it at the beginning, the tab here isn't activated. So you have to go in the data file summary, right click, and click on post process. And now your results will be loaded into this post processor. So I think it still use Paravis probably behind, but it will show you the result in a much more easier way to display. So result now I'm looking at the results. And what I'm looking at right now is the flux. So I prefer to look at the temperature. And as you can see here, temperature temperature is like this. So let's have a quick look at how to view the different components that I calculated. So if you go in component here, so here you have only temperature because this is a scalar. If we look at the flux, at the ghost point, you'll have the flux into X, Y, or Z direction displayed here. So let's go back to temperature. Now we have some mesh group filters. So this is pretty nice if you want to look at only one part. So for example, if you activate that and you want to look only at the heatsink volume, so you have to double click here to see the eye and click and apply to see only this part. So this was something that previously with Paravis you had to create filters and all this to obtain this. Now it's pretty easy to do this, so which is very nice. So I'll display the full model again. In display you have option like changing the opacity and viewing the surface edges, which is also very nice. And you can change the color bar. You can put some units in the color bar here. You can change into categories of colors. So here I have only two categories. So you can set up some categories here and make it making a non-continuous type of plot. And you have also some option for the animation. So now you have the min and max option. You have also some options here which will show you with a dot where the maximum temperature here is. So you see the maximum temperature appears here on this chip at 147 degree, and the minimum is up here at 51 degree here, because obviously this is the part which is cooled down by the convection. Now I couldn't find the option to view result at one specific point, so I think maybe this has not been implemented yet in this post process. So the way to see this is basically to still use Paravis. You still have the same post process than before. If you go to case view, right click in data file, where is it? History view, and post process browse directory. Okay, so I don't see it here. So you can just open the Paravis module. Yeah, and your result will be automatically loaded into it. So this is how you view it the old way, let's say, which is not so old, but and if you want to look at the result at one point here into Paravis, you have to first you have to have the selection display inspector activated. So if you do not see this window here, you can activate it here in View, Windows. Then select this raster temp. And now that you have that, you can go on this very small icons here and you have interactive select point on. Select this and now you're able to put some points like that and put some probe wherever you want on your model, which is pretty cool. And now you're ready to take some screen captures and to basically get all the results that you need from the simulation. So that's all for this video. I hope you enjoyed it and that this was useful for you. If you have questions, if you have things you want to see or you don't understand, leave a comment either on YouTube or on my blog and let me know. If you want to see something else next time, I'm always happy to create new tutorials. And don't forget to give a like to this video because it took a lot of time to create. And thank you again. See you in the next videos.